Hi students, you are welcome to the continuation of our physics tutorial class from your favorite student ScoreBooster, your online tutorial provider on JAMB, WAEC, NECO, NAPTIP and NAPTIP exams. Today we shall be discussing simple harmonic motion, which is a continuation of concept of motion and Bangbade A. Now, before we proceed, we need to consider the learning outcomes, which goes thus. At the end of this presentation, listeners should be able to define simple harmonic motion with examples. Also, listeners are expected to be able to explain the period of an oscillation, and also they should be able to define the frequency of an oscillation, and lastly they should be able to solve relevant UTME questions relating to simple harmonic motion. Now, when we talk of simple harmonic motion, that is SHM, it is the oscillatory, that is to and fro movements, in which the acceleration A is directly proportional to the displacement x from the equilibrium position and is directed towards the position. Now, for a body undergoing simple harmonic motion, then acceleration A is equal to minus omega square, where omega square is the constant of proportionality and omega is the angular velocity of the motion. Now, having understood the definition of simple harmonic motion, the next is to consider the examples of simple harmonic motion, and this includes the movement of an helical string. Also is the movement of a simple pendulum. Also, we have the movement of heartbeat. Then the movement of a loaded test tube also move in to and fro manner, which is up and down when it's suspended. So that makes it an oscillatory motion, which is simple harmonic motion. And lastly, you have movement of jita string. So when the jita string is plucked, then it is an example of simple harmonic motion as it moves to and fro. Now let's look at this sketch representing various positions of a simple pendulum when suspended. The point A represents the stationary or the rest period of the simple pendulum when no external force is applied, so and it's not moving. While B represents the maximum displacement. B and C will represent the maximum displacement. So now the next thing to consider is the times in SHM, that is simple harmonic motion. And the first we shall be considering is the amplitude, capital A, which is the maximum displacement from equilibrium position. Its unit is meter. Then, having understood amplitude, the next term to consider is the period T. Period T is the time to complete one cycle of oscillation. Its unit is seconds. Then the next time to consider is the frequency, which is usually represented by small f. It is the number of cycles completed per unit time. Its unit is x or per seconds. Then it's very important to take note of the relationship between the period and frequency. So period equals 1 over frequency, and also frequency is equal to 1 over period. So we have to note this. Now, the next thing to consider are the parameters of simple harmonic motion. And the first we shall be considering is omega square. Omega square is a parameter. Then under the helical string, which is an example of simple harmonic motion, omega square is equal to k over m, where k is the constant of proportionality and m is mass. But in under simple pendulum, omega square is equal to g over l. So we have to take note of this because of the importance in calculation that we shall be meeting later. Then the second parameter we want to consider is the period t of an oscillation, which can be expressed by as 2 pi over omega. If you can recollect from video 5, that is on centripetal motion, we said omega is equal to 2 pi over t. Then if you want to make t the subject, that will give us t equals 2 pi over omega. Then this period now under helical string can be expressed as t equals 2 pi root m over k, while under simple pendulum it can be expressed as 2 pi root l over g. So under helical string, period t is equal to 2 pi root m over k, while under simple pendulum it is 2 pi root l over g, where g is acceleration due to gravity and l is length. And finally is on frequency. Frequency can be expressed as omega over 2 pi. Also, if you recollect from a previous lecture on centripetal motion, that is our video 5, we said omega is equal to 2 pi f. So if you make f the subject, then the frequency f will be omega over 2 pi. Then the frequency under the helical string will be expressed as f equals 1 over 2 pi root k over m, that is opposite of period, or you use 1 over 2l root t over m, 1 over 2l root t over m. But under the simple harmonic motion, the frequency can be calculated as 1 over 2 pi root g over l. M in this case is mass in kilogram, g is acceleration due to gravity in meter per second square, l is length in meter, small l is length in meter, capital L is mass per unit length, k is force constant, yt is tension. Now let's consider sample questions from the UTME. And the first question we shall be considering for today comes from 1979, number 7. And the question goes thus: if in a simple pendulum experiment the length of the inextensible string is increased by the factor of 4, its period is increased by the factor of dash. So we are given option A to be 4, option B to be pi over 2, option C is 1 over 4, while option D is 2 pi, and option E is 2. Now, the first thing is to write out the given parameters, and from the question we are given that the new length is 4 times the former length. because they said the string is increased by a factor of 4. So that means it's 4 times the previous sum. Then they are now asking for the period. What would be the period? So in solving this, we have to recollect the formula for period, which says t equals 2 pi root L over j. So for this particular question now, they are relating length and the length with the tension, with the period. They are relating the length with the period. For example, they gave us the length and they are asking for period. So from the equation, the relationship between t and L can be deduced to be the period t is equal to root L. So when we have more than one, when you have more than one period and more than one length, then that will lead us to the formula T1 over T2 equals root L1 over L2. Let's substitute now our T1. They ask us to get our T2 in terms of T1. So, and in getting this, it will be T1 over T2 equals the ratio we are given. That will be 1 over 4. Since they said that L2, that is the new length, is 4 times the former length. So if we substitute, that means L2 is equal to 4L1. So if we substitute in the equation, then it will give us T1 over T2 equals root L1 over L2. But since L2 is now 4L1, then we can cancel out L1, L1. We'll be left with T1 over T2 equals root of 1 over 4. And root of 1 over 4 will give us 1 over 2. So if T1 over T2 is equal to 1 over 2, then we can make T2 the subject or cross multiply. So you have T1 equals T2 will be equal to T2T1. T2 will be equal to 2T1, making option E the correct answer for this one. Now, the second question we shall be considering comes from 1984, number 23, and the question goes thus: a simple pendulum of 0.6 meter long has a period of 1.5 seconds. What is the period of a similar pendulum 0.4 meter long in the same location? So you are given option A to be 1.5 root of 2 over 3 seconds. Option B is 1.5 root of 3 over 2 seconds. Option C is 2.25 seconds. Option D is 1.00 seconds. While option D is 2.00 seconds. Now solution. The first thing is to write out the given parameters, and from the question we are given length 1, L1, so which is 0.6 meter. Then we are given the period 1, which is 1.5 seconds. Then they say what is the period of a similar pendulum of 0.4 meter. That means the length 2 is now 0.4, while the period is unknown. So also we have to recall that the period t is equal to 2 pi root L over g, and from here now that means time is directly proportional to length. So we can infer that time, the period t, is directly proportional to square root of length. So if we bring that one out from the formula, you have t equals root L. So when we have more than one period and one length, then it will lead us to T1 over T2 equals root L1 over L2. So our T1 now has been given to be 1.5 seconds over T2, which is unknown, then equals root of L1, that will be root of 0.6 meter over root L2, which is 0.4. Then we can cross multiply. If you cross multiply, then you make T2 the subject. So we arrive at 1.5 root of 2 over 3. Or if we decide to cross multiply, then crossing multiply will lead us to 1.5 root 0.4 meter equals T2 root 0.6. Then make T2 the subject by dividing both sides by root of 0.6, and that will give us 1.5 root of 0.4 over 0.6. So we can divide numerator and denominator by 0.2. So that will now give us T2 equals 1.5 root of 2 over 3 seconds, making option A the correct answer for this question. Now the next question we shall be considering comes from 1988, number 4, and the question goes thus: a piano wire 0.5 meter long has a total mass of 0.01 kilogram and is stressed with a tension of 800 Newton. Calculate the frequency of the wire when it sounds its fundamental notes. You are given option A to be 200x, option B to be 100x, option C is 4x, while D is 2x. Now solution: the first thing is to write out the given parameters, and from the question you are given the length small l, which is 0.5 meter. Then we are given the mass, which is 0.01 kilogram, and you are given the tension to be 800. So from L and M we can get a capital L, which is mass per unit length. That will be mass over length, which is mass M, which is at 0.01 kilogram, divided by L, which is 0.5 meter. That will give us 0.02 kilogram per meter. Then we have to recall the formula for frequency, that frequency equals 2L root T over M. That's the formula of frequency, linking frequency with the tensional force. So we have F equals 2L root T over M, and when we substitute, that will be F equals 1 over 2 times L, which is 0.5. Then root of tension T, that is 800 Newton, divided by M, that is mass per unit length. So divided by M, which is 0.02. Then 800 divided by 0.02 will give us 40,000. So, and our F frequency F will now be 1 over 2 times 0.5 will be 1. Then root of 40,000 will be 200x, making option A the correct answer for this particular question. Now, we have some questions for your own practice. The first question comes from 1987, number 3, while the second question comes from 1988, number 29. Then we have the third question from 2000, number 18, and the fourth question from 2013, number 5, and the expected answer has been put there for your try. Our next video is going to be on energy with sample questions from UTME and their solution. I urge you to please subscribe to our YouTube channel, like and share our videos, as we promise to be giving you more interesting lecture on subjects related to UTME questions. Thank you.